just give you an update about the work that you did in DSEQ. And I should be finalizing the assessment and the review on your first deliverable. No matter you are doing the COVID data analysis or the DSEQ, right? And I'm going to show my screen so that you get some idea about how your work will be studied. Can you see my screen right now?
Yes.
Okay. All right. So your work is study and review not just by me, but also a PhD student. And specifically, this is what I asked the so-called TA to do. So I did not tell the TA whether you are graduate or undergraduate, and I gave him 5 levels, right? Undergrad, junior, undergrad, senior, first year grad, second year grad, and third year grad. And the quality review will be 5: poor, fair, good, very good, and excellent. And the way that it works is I told him to initially sample 2 or 3 deliverables, right? On the DSEQ and COVID data, we don't have much to do that exercise since there are only like 3 entries for the COVID data analysis. And what I asked him to do is to take 2 and 3 so that he can calibrate himself about the group. And I did not tell him for each deliverable, is it coming from undergraduate or graduate or the graduate center? And what I asked him to do is read your deliverable. And based on his experience, think about whether that deliverable is coming from an undergrad or a graduate. And if it's undergrad, is it junior or senior? If it is graduate, is the first year graduate study, second year graduate study, or third year graduate study? And I also asked him to give a quality review according to the criteria we discussed in the class, not about copy and paste if you're doing a DSEQ paper, but really to discuss what you learn from the paper, what you understand, and particularly what you do not understand. And based on that rubric, give a quality assessment for that, right? And not only to do that once, but to do that initially once, and then do it again to see whether there may be a discrepancy, right? So that it would try to minimize the bias subjectivity simply because it's a one-off, right? And if on the second review, it may not have the same conclusion, then he is welcome to put it down. And whether he is very harsh or very generous doesn't matter. The way that it will work is now he turned in the level assessment and the quality review for the first attempt, and the level assessment and the quality review on the second attempt. Then ultimately, if you are undergraduate and he thinks that you are a graduate student and your quality is high, that means you did a great job, that you are performing at a graduate level and producing high quality work. If he thinks that you are a graduate student, but your quality is not that great, then essentially that will come back to say, well, maybe for undergraduate, this is more acceptable. And in reverse, if you are a graduate student and his impression about your work is undergraduate and the quality review is low, then there's an issue there. right? So that you kind of like get an idea about how this metric works. And after that, we will be I will be computing the z-score. So therefore, it doesn't really matter whether he is harsh, and just give everybody, say, a fair or a poor or a good. And essentially all the numbers will be normalized using z-score. That would remove and minimize the internal bias. And if the best you get is good, the worst you get is poor, then essentially it becomes 3 buckets instead of 5. Right? And if everyone is excellent, the worst is very good, then probably will be normalized down, as opposed to the other extreme that would be normalized up, right? And in that normalization process, it also depends on the distribution, how many are close to the mean, and what the variance of the distribution look like. So that would be something that would inform, right, about overall performance of the class, right? So that would be the way that your first deliverable has been studied upon, and the same process approach will apply to the final deliverable as well. And for the second one, it will be on the weekly basis. What you turn in your quality analysis and result when you make the prediction, so that that piece we will not have this lengthy process to go through that. And it's also a little bit slow to get back to you guys about this because I'm spreading between the DSEQ and the data COVID data analysis, and also I need to onboard the PA so that he would get used to a practice and a metric that would be as impartial as possible about this, right? So that is how your first deliverable has been studied upon. Any questions about this? So that when you get the result, right, you would not be a surprise, say, oh my God, what happened to me? So that you can put in perspective. And if you did not turn in your best effort work, then no matter what, it won't cure the problem, right? So I just want to make that part clear. And if you have made the best attempt turning your best quality work, you should not need to worry about, I thought that I worked 10 times harder than any other classes, how come I get a fail, right? Because that may just simply happen when the PA is looking at the entire class. He just has not been impressed by anybody, therefore fail may be the best grade, right? I'm not saying this is the case, but I'm just telling you all these different scenarios so that you can better understand, right, about whole process on that. And this is not about gaming the system, copy and paste, turn something in, and hoping that nobody read and you just get an A. So we did try to put in some effort to learn how we are doing and how you guys are doing at the same time. And this process also helped me to understand from student perspective, like him, right, what he considered as an acceptable standard among peers, as well as what kind of bias a student TA may introduce, so that we can kind of like go back and adjust that. So any questions about this before we move on? All right, so if there's no more question about this, so we will move on. And so the other thing that I do want to mention to the class is that since we are doing it online and quiz final exam is not an option. So therefore, at the end, the most we can do in an online class is to have activities that would need the assumption students are doing their part, right? And if a student decide not to do anything, that really is not much like anybody can do, even in the in-person class setup. That being said, the assessment evaluation will be a lot harder. And I thought about this whole process since this semester is the first time the entire semester will be online. And I think the conclusion that I ended up to have after factoring in that you guys are also busy with other classes, your life, and probably also under stress with COVID and many other related things that were impacted by COVID. So I think the expectation is if you are in this class, you need to demonstrate that you understand at least one topic, one concept well, right? If you want to pass the class. So that would not be, I am just going to copy and paste something, or I'm just going to have other people do the work in a group for me, or I'm going to propose something totally irrelevant, right? That I did it for the other class or for some other means. So that would not cut it. So if anything that I mentioned along that line is what some may have been thinking about, you may want to reconsider that, right? Since we are halfway through the semester already. So I just want to make sure I mention that before it is too late, right? And if you are not aware and thought that this is the way to go, and then at the end of the semester, there may not be enough time to come back to rescue that. And I mentioned that because I saw a few things from your first deliverable and the interaction in Piazza about this. So I thought that it probably is worthwhile to spend 10, 15 minutes just to bring this one up and put it away, right? Especially we're getting into the most difficult part of the most difficult topic for this class this semester today, right? And is that part clear to everybody, right? If anybody has any questions, let me know. So what I do plan to do is to go back to our discussion, right? And let me just quickly pull out where we left over last time. And we can build upon that for today's discussion. Can you see my screen?
Yes.
Okay. Now, so we started out with this simple example in the book, right? Two constraints that we formulated as a linear algebra problem, and the way to find the solution, right? Multiple probability models is that let's use SVD to find a first initial solution. And the way to do that would be to formulate your facts, right? Your ground truth as just equality constraint. And if not, we can always convert it into equality constraint. And then from that point on, we just plug in SVD to find out the U matrix, diagonal matrix D, and the V matrix, and then we reverse the process to find an initial feasible solution. And then at that point, we say, yeah, there's an important finding that you guys can get extra credit, and I'm surprised that no one single person attempt. This actually is not a hard one. That if you look at the II entry of the diagonal matrix, if it happens to be 0, then your corresponding I column in the matrix V is actually a null vector. And with this important observation here, then what you can do is, if you are going to generate multiple solutions, if your problem is an underdetermined linear algebra problem, then algorithmically, the way that you can generate multiple solutions would simply be just taking the initial solution X and then do the linear combination with a null vector multiplied with some constant, right? And every time you change a constant, you change the entire vector, which is still yet another solution for your original problem. And therefore, SVD offers a neat idea, right? That you can actually code that to find multiple solutions if you have an underdetermined system. Right, so that's where we left over last time. And what we want to continue is go deeper into this. And this is also something that I would encourage every one of you to pay attention to, that it is not about just learning some technique and you really do not understand, just like plug it in and use it. And in the good old days that we actually have to write code for that. And nowadays, you don't even need to write the code for that because they're already like libraries. You can just call and use it, right? Or online calculator, that what we were doing. So therefore, the trend is your generation tends to get exposed to a lot more different concepts, but may not be going deep enough to really understand when, how, under what circumstances, what should be applied, right? And that's what I observe as time progresses, like last few years, 5 years, 10 years, 15 years, 20 years, this is what has been happening. And I think that would be worthwhile to point it out, and you guys should pay attention to, is if you want to learn something, say this or anything, right? Try to go as deep as you can on the conceptual level and ask the right questions. And if you are willing, if you're not willing to spend time and effort to do that, most likely what will happen is just the trend majority that I observed. They will be able to quote a pretty fancy jargon and term. But when you really dig deeper and ask them the rationale and that concept, they can't explain, right? Or you tell people you have taken data mining class, people ask you what did you learn in data mining, what is data mining? And if you can't go further into a discussion like that, then that becomes a gap, right, that you don't want to have. So in this case, if you really go deeper into this, there are actually a number of issues that you really need to address in order for this idea to work, or at least you know how to get around it. And the first observation is, if you look at how we calculate or derive a first initial solution, right? The way that we did it was that we take the matrix A and then we decompose into 3 matrices, and then we just simply multiply V matrix, the inverse of a diagonal matrix, and the transpose of a U matrix and the constant vector to get it. If you look at this equation here, or this step says nothing whatsoever that every element in the vector X must be non-negative. It didn't say anything about that. And yet, if you look at our original problem, that what we were trying to solve, we want every element in your vector to be non-negative because these are probability terms, and we need to observe the probability axis, right? So therefore, if you ended up getting a first initial solution that not all the terms, right, are non-negative, then what ended up happening is this, and listen carefully for that, right? You get a solution for applying the SVD to solve the linear algebra problem, but that solution is not good enough as a solution for the problem that you intend to solve, which is to derive probability model, right? And in this simple example here, we got lucky that the initial solution we found actually is a vector, that every entry is non-negative. So therefore, this is a qualified solution from the SVD for your algebra problem, and that solution also happens to be a solution for the problem that you intend to solve, which is to discover probability model. Is that clear about this concept? And to drive home about this point, before we take a break, for you guys to digest that, is when you get to generating multiple solutions, right? You change what? Now, the first initial solution vector is fixed. Your column vector from the V matrix is fixed. What is not fixed is your constant. You can choose different value of constant to get yet another solution, such as you can pick, say, C is equal to 0.1, and then when you calculate this, you get a new vector different from X, which is yet another solution, and you pick another value for C, and then you get yet another solution, and keep doing that. Now, but in this case, right here, you can see if you just simply pick C equals to, say, 1, right? Then right away, you are going to push the first term to become negative. Therefore, at that point, what you generate is a solution, which is a legitimate solution for your SVD linear algebra problem. But that solution, unfortunately, will not be good enough as a probability model for your original intended solution that you try to solve, right? So therefore, in the process of doing that, not any choices of C will be acceptable. And in a worst case, your initial solution may not even be a qualified solution for your original problem, when some of the terms in your solution vector may not be non-negative, right? And there's no guarantee in using SVD that your initial first solution will be non-negative. Then now the question becomes, if they are not, what are we going to do? Then how good is this idea? And the answer for that is, fortunately, we are okay, because there is an algorithm called Kurzgesagt and Schender, and you can actually use this other method in conjunction with the SVD that will guarantee you that if you properly formulate your linear algebra system equations, and if there is at least one solution, you can always find an initial solution that is not negative, and that part is guaranteed, right? And what we're going to spend time today is to actually go through this, so that you know how this works. And in the past semester, I did have students ended up writing code to implement this, and if they turn it in, they definitely get a reasonable share of the extra credit for that, because this is not obvious. But the concept is definitely approachable and comprehensible by undergraduate students like you, because these were done by students in the past for this class. All right, so what we're going to do is to spend next half an hour or so, right, to go through this method, so that you know how you can apply this to guarantee to get an initial non-negative solution. Any questions before I go further? Now, I will be making assumption that you at least put in the effort to catch up on the class note, what we discussed for chapter 9. And if not, then the utility today for you is going to be probably like 10-20% only. The algorithm was discussed in the class, but not an illustrative example, right? The illustrative example here, I don't remember, I don't think it's in the book, it's more like an appendix. And we will go through that. Maybe we make that as an extra additional homework for the class just to make sure that you know how to do that, right? Because this part will be critical to your understanding about the concept in this topic. All right, but the algorithm is briefly described in the book, but without an example that may be hard. Therefore, to respond to Nicola's comment, we'll go through this example, or maybe make that as a extra homework for the class to do, just to make sure that you know how to do that. All right, and all right. So, how does this method work? This method works in the following way. Before we talk about how this method works, what we want to do is to go back to revisit the basic concept, right? So what are the basic concepts? First, what we have done so far is saying that we can formulate that as a linear algebra problem. And from the concept in linear algebra, if you have 3 linearly independent equations and 5 unknowns, then we know this is what we call an underdetermined system, and you can have many, many solutions, right? And one thing to keep in mind and to emphasize is we are talking about linearly independent.
Professor, did you share the screen or?
Oh, thank you. I totally forgot that I need to share the screen. Yeah, sorry about that. Right, so let me make this part clean, right? Just copy this so that it would not too busy. Okay, so the first thing that you need to keep in mind before we even get into discussing something further is make sure you are not overlooking the basic concept in your linear algebra math class, right? So whatever you put it down as an equation, as one of the equations for your linear algebra system, right? That we want those equations to be linearly independent, meaning that you are actually not allowed to do this, right? So you can't make things out of the thin air. So you are not allowed to do something like this. So you can't just make things out of the thin air, say, yeah, I can just add these other 2 equations. Therefore, right now, I have 5 equations, 5 unknown. I should have only 1 solution. And the answer is no, you're not allowed to do that. Because if you look at equation 4 is nothing more than just take equation 2 and multiply by 2 on both sides, right? And equation 5 is nothing more than just equation 3 and multiply both sides by 2. And therefore, in theory, you can add as many equations as you want, but that doesn't change the nature of the problem, which is underdetermined. Because the way we determine what is underdetermined is that whether or not all the equations are linearly independent, meaning that you cannot try to express any equation, right, using the combinations of the others. And that's the basic requirement. Now, and if you ended up not careful and inadvertently introduce equations that are not linearly independent, then even though the algorithm in theory should work, after the implementation, it may not. and you may get unexpected behavior and result simply because that at that point you are pushing your program or the algorithm, right, to work on a what we call a degenerative case, and a degenerative case will have at least the consequence, right, that your determinant is 0, and then you know the system is degenerative. Then there are a whole bunch of other unexpected behavior that would happen, right? So therefore, in the conceptual level and the theory side, it works. But in the actual practice, if you write the program and precisely implement that, and it should be working, but that would not cure if you are not careful with your constraint formulation, right? So that's one thing that you need to keep in mind. And in the application level, if you think that there should be a solution, but at the end you didn't, often is this kind of the problems that have happened, right? So just make a note for that if you may end up, say, using this for your second deliverable. Now, okay, so now go back to where we are, right? 3 equations, 5 unknown under determined system. And the concept here is saying, if we just apply SVD, we may not find a initial solution that is non-negative. So therefore, we want to find a cure for that. And the idea to do that is to actually introduce additional equation constraints, right, while they will still be linearly independent. And the way that you want to do that is saying, I'm going to introduce something called Z0, an additional variable, and the Z0 should be equal to 0.65 minus P0 minus P1 minus S. All right, so, and the way that I make this one up is simply by moving all the terms, say, from the left-hand side to the right-hand side, and then call that expression equal to Z0. And therefore, in effect, I'm introducing an additional variables and an additional equation constraint into my linear algebra problem. And I do the same thing for C1, which is 0.52 minus P0 minus P2, right? And it's the same that I do the third, Z2 is equal to 1 minus P0 minus P1 minus P2 minus P3. So far so good, right? So now I want to add these 3 equality constraint into my linear algebra problem, so that right now the problem that I need to solve, right, is no longer 5 unknowns, 3 equations, but instead is 8 unknowns, 6 equations. Right. So what are the 8 unknowns? Would be P0, P1, P2, P3, S, Z0, C1, and Z2. Right. So therefore, right now, instead of solving the problem with 3 equality constraints, and now what we want to do is to solve a new problem that has 6 constraints and 8 unknowns. So far so good. Are we okay with that? Now, and what we want to do is to look at this, right, and say, what if we think about this as an optimization problem? Now, if your original problem is underdetermined, right, then you expect to have multiple solutions. And you can always ask the question when you go dig deeper to understand what we were trying to do is that if we have multiple solutions, are all the solutions equal, or quality-wise, some may be better than the other? And when we say quality-wise, some is better than the other, how do we approach that, and what do we consider when we say quality, right? And this is a classical optimization problem concept that we always talk about. So therefore, in this case, when we reformulate that as a new problem, right, that now we have 6 equations, 8 unknown, we have multiple solutions. We do want to think about what is a solution with what quality, right? And the way that we would think about that is that, say, we want to introduce a cost function, right, that would allow us to know the quality of the solution. And we say the cost function that we want to use to evaluate is just simply Z0 plus Z1 plus Z2. Now, you can pick any other cost functions that you want. Now, but for the purpose of this particular algorithm that you can take advantage on to guarantee you that it would help you to find an initial first solution that is non-negative, right? The cost function you want to have will be the sum of all the additional variables that you introduced into the system. Now, and if this is a cost function, then we want to have some concept about is the larger the value, the better, or the smaller the value, the better, right? And in this case, we want the quality to be inversely proportional to the sum of these 3 variables. Therefore, the best quality solution we want to get is actually the minimum of the sum of these 3. Right? So now let's think about what does that really mean if we do that. So if there's a process that you can find many solutions right here, and you evaluate the quality of the solution according to this cost function, and your objective is to find the best solution. The best solution means the solution that will minimize the sum of Z0, Z1, Z2. Right? Now if you take one step back and think about the problem that you're trying to solve and the requirement, what is a requirement? We say we want every element in our solution vector to be non-negative, right? That's why we ended up using this, because SVD may not guarantee that. And in order for a solution qualify as a solution for this problem, then what you are really saying is that P0 has to be non-negative, P1 has to be non-negative, P2 has to be non-negative, P3 has to be non-negative, S has to be non-negative, Z0 has to be non-negative, Z1 has to be non-negative, and Z2 has to be non-negative, right? So now here is the trivial question for you. If this is the case, what is the smallest minimum number you can get for the sum of Z0 plus Z1 plus Z2?
Is it
0.
0. Now, when and how can you get a 0 for the sum of these 3?
Well, everything you get correct.
Say again? When?
When you get everything the correct answer.
Do you know the value for Z0, Z1, Z2? So that the sum of the 3 will be 0?
When they all have to be 0?
When each has to be 0. Because we say each of this has to be non-negative, right? If all this has to be non-negative, you cannot bank on cancellation effect, meaning some is positive, some is negative to make it to 0, right? And if they have to be all non-negative, then the minimum for the sum of the 3 terms has to come from the minimum for each term. And the minimum for each term as a non-negative has to be 0. That makes sense? Now, this is important. We're going to talk about next. Let's think about the optimal solution? Let's think about the optimal solution. We say the optimal solution will be coming from, no matter what happens, Z0 is equal to 0, C1 is equal to 0, and Z2 is equal to 0, right? Now, if Z0 is equal to 0, what does that mean? If you look at the new equation you introduced, it means this is equal to 0, right? It means this is a true statement. Agree? And Z1 is 0. What does that mean? Well, it means the same. This is equal to 0, therefore, this is equal to 0.5.
那 zero 就是 come back to C1 to 3, right?
I'm sorry?
When z is equal to 0, you just go back to C1, C2, and C3.
That's right. And that's the key part. Why this is the key part? Because what you are saying is that
Oh, Professor, I think your voice is breaking up.
so you cannot hear me well right now?
No, there is some breaking up in your voice. It's like we hard to hear what you're talking about. Yeah.
All right. So I think this is the same problem here. That I have to call in. It probably is because of the number of users here. I'm going to get out and come back in in a minute, right? So just bear with me so that I can call in. And Anthony, when I come back, you just pass the control back to me.
Can you hear me right now? Okay, cool. All right. All right, so let's get back to where we are, right? On this. So we say if you can find the, oh, sorry, I need to share my screen. We say, you can see my screen, right?
Yes.
Okay. Now, when we say you found the optimal solution, then you have this. Let's think about what that means. We say we started out with a problem that we try to solve, and that problem is to discover a probability model. But in order to solve that problem, we are not really trying to solve that problem directly, and instead we try to formulate that problem as a linear algebra problem. And in doing so, we take advantage on the hard work other people have done, which is singular value decomposition. And by formulating your problem as a linear algebra problem, then now we take advantage on the hard work people do in inventing the SVD. We just plug it in and use it, right? And it's a neat idea. But unfortunately, the SVD has its own limitation too. It does not guarantee it always find a solution for your original problem, even though it guarantees to find a solution for the linear algebra problem. And when will it not be a solution for the initial problem? When you have negative entry in your solution vector. And therefore, to have a remedy on that, we say, let's go in and look into the yet another algorithm, right? And see whether that would help us find a first initial non-negative solution. And for that, the idea is to solve yet another problem from our initial problem one that we formulated as a linear algebra problem, which is problem 2, and then from problem 2 that we introduce problem 3. And then the problem 3 we introduce right now here is that instead of thinking about that as solving a linear algebra problem, we want to think about this as solving an optimization problem with a cost function like that. And we say when we get to the optimal solution, Z0 is 0, Z1 is 0, Z2 is 0. And if we are able to achieve that, then whatever you have for P0, P1, P2, P3, and S, right, would naturally satisfy these 3, which is actually what you're looking for in your initial problem, problem 1, right? So therefore, now the focus is that how do we take advantage on what we know, right, to solve this particular optimization problem, right, is what essentially the KTZ algorithm is offering us. And the way to do that is actually just a simple visualization and using the data structure about table that you learn in either junior year or sophomore year already about this. So how do we do this? The way that we would do this is the following, right? We say, yeah, we're going to introduce the 3 variables, right? And when we introduce the 3 variables, we're going to put that into a table format like this. And what you see on the first row, right, essentially is just Z0 plus C1 plus C2. Now, remember we say what we want to do is to minimize Z0 plus Z1 plus Z2, right? Now, and if you actually plug in, right, Z0 as this guy, this is your Z0. This is your Z1. and this is your Z2. And when you regroup all this together, then what you get is this guy, 2.17 minus 3 times P0 minus 2 times P1 minus 2 times P2 minus P3 minus S. So far so good, right? So therefore, to minimize Z0 plus Z1 plus Z2 is the same as what? That we want to minimize this guy. And to minimize this guy is the same as to maximize the opposite of it, right? So the opposite of it will be just minus 1 times the whole expression to give you this. So far so good. And once we have this, then we want to make up a table, right? We just label this column 1, 2, 3, 4, 5, 6, 7, and then we have row 1, row 2, row 3, and row 4. And in row 1, we just simply copy over our cost function, which is minus 2.17, minus 3, the coefficient. I'm sorry, 3, our coefficient, 2, our coefficient, 2, our coefficient, 1, our coefficient, and 1, our coefficient. And then we fill out the rest of it. What is Z0? Well, we say Z0 equal to 0.65 minus P0 minus P1 minus X, right? So therefore, we have 0.65 minus 1 for P0, minus 1 for P1, nothing for P2, nothing for P3, and minus 1 for S. And for Z1, we have 0.52, right? Minus 1 for P0, minus 2 for P1. And for Z2, we have 1, right? Minus 1 for P0, minus 1 for P1, minus 1 for P2, and minus 1 for P3. Is that clear how to construct this table from your constraints here so far? Right, so essentially we're just rewriting the linear algebra problem that you have without doing much of anything.
Professor, again, why do we maximize Z after we minimize it?
Well, we try to minimize Z0 plus Z1 plus Z2, right? But when you try to minimize this, which is the same as minimize this. Now, to minimize this is the same as to maximize the opposite of it. Did you get the idea?
I think so, yeah.
Right. So if the number is positive, you try to minimize the number, which is the same as what? You look at the negative version of it on the negative state, you try to maximize it, right? It's the same concept here. Because it doesn't change anything. Right? So if now you rewrite in this form and get to this table, what do we want to do with it? What we want to do with it is the following. We are going through iterations, right? In each iteration, we're going to find a pivot. Say you want to find an entry, say here, for example. If you pick this entry here, this is row 2 and column 4, right? If you decide to pick a pivot here, then what we want to do is to rotate the position of row and column. So that you want to move, if you pick, say, row 2, column 4 as a pivot, then you want to rotate P1 to here, and then you want to rotate Z0 to here. Is that clear about this? All right, so that you should keep in mind, that's what we're going to do. Okay, so therefore, the iteration is going to be, we're going to look at this table. We are going to come to this table to look for choices that we can use as a pivot and find the quote unquote best one, and then we are going to rotate row and column. All right. Now, before we actually do this, and to talk about how do we pick a pair and rotate them, let's try to get a hang on what does that really mean, right? When we are rotating it. Hopefully, if we do a simple example, that will help you see through the intuition behind it, right? About what we were redoing here. Now, for the sake of argument, right? Let's say we are going to pick row 2, column 4 as our pivot, meaning that our intention is to rotate P1 down here and Z0 up here. All right. So now what we want to do, hopefully I have enough time to do all this. See what I can do. Do it a bit faster like this. Oh, good. It works. All right. So what we want to do, we say, this is the guy, right? We say row 2, column 4 is the one that we want to pivot. And if we want to pivot this, what we hope to get eventually, what we want to get eventually is something like this. Your Z0 is up here, and your P1 is down here. Now, but we can just simply say, exchange these two guys, right? Because once you exchange these two guys, all the numbers here are going to be different, right? So you will have to go back to reconstruct this table at that point. Now, how do we go in and to reconstruct this table at that point? So we are actually going to spend time to do that. Right. Today we may not have time to actually talk more about your second deliverable, and because we are going to push back 3 days for the kickoff, so therefore we are not going to officially launch until probably like Sunday to have the data and the subjects ready. So we'll talk more about that on Tuesday, and then I'm going to spend the next like 20 minutes or so, 15 minutes or so, right, to just go through this example so that you have something that you can go home and read it over the weekend. Now, if you're going to swap Z0 and P1, right? So what exactly is happening here? What exactly is happening here is that in this particular equation here, your P0 is on one side, right? And on the other side, it becomes 0.52 minus P2 minus Z1. Agree? Now, you guys need to stay with me and follow the derivation. Otherwise, you're going to get lost on that. Once you swap these two guys, right, now you can fill in the second row. Now your second row is going to be 0.52. Right? You don't have P0 anymore. You don't have P1 anymore. One anymore. Did I say P2? Did I miss something here? Oh gosh. What do we would say Z0 and P2, right? So this is actually P2. Sorry for that. Right. This is P2, 5.2. P0 and minus Z1. So therefore now your P2 is 0.52, right? Your P0 is minus 1, and nothing else here. You have a minus 1 here, and everything else is 0. Oh gosh, I apologize for that. What did I do wrong? Did I say Z0 that we want to swap? Okay. My bad. I look at the wrong equations here. So what we want here is to swap P1 and Z0, right? Sorry about that. P1 and Z0. So now Z0 is up here and P1 is down here. Right now, so when we do that, then now we have P1 is equal to 0.65 minus P1 minus S minus Z0. We actually don't have P1 here. So that's okay. Right, so we're just rearranging the terms, right? We move P1 to the left-hand side. I'm sorry?
You have P0. Why you don't?
You forgot P0.
Oh, yeah. Okay. Yeah. Thank you. Right. P0. Right. So P1 is equal to, we move P1 on this side and move Z0 to the other side. We have P1 is equal to 0.65 minus P0 minus S minus Z0. Right. And then what we're going to do at that point is now here you can go back in and fill this guy up. And now you have 0.65 here. And you have minus 1 here, and you have minus 1 here, and you have minus 1 here. Agree?
Yes.
And then what we're going to do is to plug this into the other equations that you have. Right? So therefore, now your Z1 is equal to 0.52 minus P0 minus P2. It was not a factor because there's no P1 term here, right? So therefore, this guy is the same. We didn't change anything. And now we are going to look at Z2, right? So now your C2 is going to become P1 is equal to 1 minus P0 minus P2 minus P3 minus Z2. Yes?
Wait, that's your second equation for P1?
I'm sorry?
You have two equations for P1 now, right? Because you have
yes. So, oh, yeah, I keep making a mistake here. So this one, our Z2 is equal to, actually what I meant is this, is to move the term P1, right, to the end. And when I move the term to the end, then what you want to do is to make the substitution here to get rid of the P1. So therefore, this guy is actually equal to this. 1 minus plus, I think. Actually, you have a minus P0. Let me just write this one out. Just do that once more, since it will be too costly otherwise. So this is minus 0.65, and this is a plus, and this is a plus, and this is a plus, right? And then if we go through that one more step, then now your Z2 is equal to 1 minus 0.65. I intentionally, I don't want to go through this process here, just want to put it that way. Minus P0 plus P0, so P0 disappear, right? And we don't have a P1. So we have minus P2, we have minus P3, we have plus S, we have plus Z0. Agree? So therefore, right now when we write, right, what is Z2? Z2 is 1 minus 0.65. And we don't have P0. We have Z0, which is 1, right? And we have minus 1 for P2. and we have -1 for P3, and we have 1 for S. So far, so good. And then we're going to quickly do this, right? The constant function right here. Do I have it in the, yeah, I want to copy to make it really fast. Okay, so let me copy this. Now go back to reconstruct your first row, right? Your first row started out with this, yes? And now what we want to do is to make the substitution by getting rid of P1, right? And if you want to do this by getting rid of P1, this is how it looks like. 2.17 minus 3 times P0 minus 2, and this step we want to go slow. Minus 2P2 minus P3 minus S. Is everybody with me so far?
Yeah.
Yes.
Okay. And I will post this in the class note, but you want to make a note, right? A few things that I would not be putting in right here. And now I'm going to regroup this. 2.17, I just copied that. I'm going to move this guy over. Okay, which is minus 2 times 0.65. And 3P0, I just copied. Plus 2P0, I just copied. Plus 2S, I just copied. Plus 2Z0, I just copied, right? And the same. 2P2 minus P3 minus S. I'm really a horrible typist. I can type. Now, and now let's group this. Minus 3 plus 2 is just minus 1, right? So we get rid of this guy. And plus 2S minus S is just plus S. Right, so therefore, this is our new equation for Z. So far, so good? So therefore, our Z prime, right? Now, take a look once more. We want the opposite of it, right? So therefore, our Z prime is just equal to this. This is negative. This is positive. This is negative. This is negative. And this is positive. And this is positive. Therefore, now if you come in and fill in the blank, this is what we have. P0 is 1, right? We have it right here. And Z0 is minus 2. And P2 is 2. And P3 is 1. And F is minus 1. So far, so good? Right, so all what we are doing is this. We started out with our table. We pick a pivot. We'll talk about how to pick the pivot next time. Right, and the purpose of taking a pivot is to rotate row and column, right? Move P1 down here, move Z0 up here, and in doing so, you're affecting the row 2, and then when you rearrange the terms, then P1 is on one side, everything else is on the other side. And in this process, because we get rid of the P1 getting to the row, therefore, we need to get rid of P1 dependency on every single row as well. And the way to do that is for every row, right? You replace whatever P1 is by the term here, right? So that after you do all the regrouping, you get something like this, right? And let's think about what that means. what we have been doing so far. Now, remember, we intentionally don't do anything right here, right? So now let's go and you should make a note to yourself. 1 minus 0.65 is a 0.35. There's a change for 0.35, right? And there's a change on the constant here. So I will talk about the consequence of this change, right, in more detail next time. But I want to point out 2 important observations before I let you go today. Observation number 1. If you think about this table, no matter is this original one or any table in this form, remember we say now you're actually solving a problem with 8 unknowns and 3 equations when we put that in the table form like this. If you have 8 unknown, 3 equations, you can do something really, really lazy, right? To just read off an initial solution for you. Now, let's take a look on this original table, right? On the first step. Your P0, P1, P2, P3, F, Z0, Z1, Z2. If you want to get a solution from this table here, all you need to do is whatever variables in the column, you just make it 0. Right? And whatever variables in your column 1 for your row, just assign a value which is equal to the constant. Then you get a solution. So therefore, for this table, right, your solution is going to be this. And this always works. Why this always works? If you just assign all the variables on the column set to be 0, right? You're just like multiplying 0 with a coefficient that's always 0, right? So therefore, what you're left with is just the left-hand side variable equal to the constant value on the right-hand side. And the same thing when we get to here, right? Now your initial solution will be, let me bring this bigger. Now your initial solution is going to be what? P0 is 0, right? Because it's up here. And what about P1? P1 is 0.65. What about P2? P2 is here, so it's 0. What about P3? P3 is also 0. What about S? S is here, it's 0. And what about Z1? Z1 is 0.52. What about Z2? Z2 is 0.35. Then now you get yet another solution just by reading off, right? The values on the constant column and assign that to the variables in your row index.
You forgot Z0, Professor.
I'm sorry?
Did you forget Z0? In the solution?
I think I did. Was it P0, P1, P2, P3, F? Thank you. Yeah. Right. We set up a 0 here because Z0 is right here. So therefore, now you can get yet another solution, right? So therefore, if you think about this process, once you have a table, you can always relog a solution, right? By just like ignoring all the terms in your column. And then now there are 2 key questions, right? One is, what guarantees that what is left in the constant column, right, excluding the cost function, is always positive? Because in this scheme, we want all the terms non-negative, right? Therefore, you want to make sure all those terms are positive. Now, and if you think about this process here, we started out by formulating before the first iteration. This has to be non-negative. Therefore, if this to be non-negative, we just need to be sure whenever we pivot and swap, right, those terms will remain non-negative, right? And as long as we can keep that, then we can just relog a solution. That's important observation number 1. And the important observation number 2 is in this process doing it, you are actually changing the value of the cost function. Right? Your cost function is just going to be equal to the constant, and then you just assign all this to be 0 essentially, right? Same concept. Now, how much change do you get from here? In this example, the change you get from here is actually what? 0.65 times 2. But wait a minute, where do you get this 0.65 times 2 from? And if you actually go back to look at this guy right here, right? Essentially is the ratio of the coefficient P1, right, your pivot for the cost function, divided by the coefficient of the pivot element. So therefore, is the absolute value of that is 2 divided by -1 absolute value, which is 2. Right? Is actually a multiplier with your constant value here, right, which is meant for Z2. This one, you swap it out, is the effect right here. That would have an impact on how this guy is going to change. That's where you get this 2 times 0.65 from. Right? And if you actually keep doing that, you will see this pattern. This guy is getting bigger and bigger, meaning that this number is going towards closer and closer to 0 when you keep doing this process, right? So therefore, the major takeaway today is that we write that into a table format, right? And if you rewrite that in table format, you can always read off a solution, guarantee every term is non-negative by just ignoring all the variables on the column. That's the mechanism about that. And the effect of rotating a variable on the column and row has an effect on the change of the cost function. And this process also guarantees you those terms will continue to remain non-negative. Therefore, this becomes an iteration that you keep doing that until you see what? This guy is 0. Right? Now, but which one you pick as a pivot would have a consequence, whether you get the optimal solution or how fast you get to the optimal solution. And that will be what we're going to talk about next class, right? So today's class, what we want to do is just to introduce this, right? So that you can start like getting a hang on from one iteration to the next, what exactly is going on. And I think this you can implement that as a two for loop, and you will be able to do all this as well that we were talking about here. And then you will need an iteration to identify the pivot, right? If you want to implement this whole algorithm. But before we do that, you kind of like need to first get a hang of the basic concept behind this first, right? It's what I'm going to leave here for the weekend to study so that next class when you come back, you will be ready for that. Sounds good? Right? Okay, sorry guys that we ran late today with the audio problem, among other different things. So any quick questions before we close it out? If you might have longer version of the question or the question may take a long answer, always email me or put in the other. Right? If anything quick, I can answer right now before we all go to the 10:45 class. Now is a good time to ask. Tuesday? By Tuesday, we'll just email that to each individual. Right, so you would be getting exactly what I show you, right? What is the level that your peer in the PhD program think that you are at, right? And the quality review. The quality review primarily is from him, right? I don't change his quality review. I would just simply use that to calculate the z-score, and I will report the parameter of the z-score for you guys, the mean and the variance, right? And then you will know what that looks like. Okay. Any other questions? All right. and if not, then I wish you guys a good weekend, and I will see you guys again on Tuesday.